Okay, so we come to quantum dynamics, right? Soumyan said quantum dynamics, so I thought I would talk about non-adiabatic interactions. He is an expert on the subject. Whatever I have learned is from him, okay? And the other person who is dealing with it is Sushanta, you will come online. So I will give you glimpses of it, right? And this has been possible because of our collaboration with Michael Bayer. And he visited IISR Mohali, spent one semester. I didn't expect him to spend one semester there. He came and we started collaborating, and he taught a course. All the students registered in the course, right, had a paper with him and me as a co-authors. So it is how important it was to have him over, and it did not stop. Our collaboration continued, particularly after he became 80. We met each other in Jerusalem, right, for his 80th birthday. After that, a lot of collaboration started. So I have lots of slides on the collaborative work, but we may not have time to go into all of them. These are some of the papers that has come out of this collaboration, and Satyajit is a main player in this field. And I don't know how many of you have seen the movie Oppenheimer. Some people are shy in, oh, you see, that side is not so shy, right? So that movie was based on that book from what I understand, and that was the thesis supervisor, Max Born. Oppenheimer couldn't finish his PhD in Cambridge because he was not good with his hands, so Cambridge, whatever that lab was called, Cavendish lab, is it? Threw him out, so he ended up in Göttingen at that time, before the Nazis came in. And he wrote this paper and scribbled and then sent it by post to a supervisor from Paris. Supervisor sat down, and the job of supervisor sat down and cleared everything and wrote the paper that finally came out. And Satyajit will say that he has worked out every equation in it, right? And I have not done. It's in German. Very difficult paper. It's a long paper. If you want to read this and ask any questions, please send it to him. Okay, and this is Michael Bayer's book, Beyond Born-Oppenheimer Approximation. Because most of the time we are comfortable with Born-Oppenheimer, that's what we do. But Michael is an authority on the subject. He came with this book, and after a few years, he came and taught a course. This was a textbook. He would open pages and pages of it in the form of a slide and taught that course. And what is the essence of this is that when you solve the Schrodinger equation, this is what you have learned in this workshop, the DFT route that you have learned to solve this problem. But if you stay with the Schrodinger equation and you write down the total wave function, which you can split in the nuclear part and the electronic part, and this separability is a basic assumption. And here, it took a long time for me to understand why this is a semicolon and not a colon, okay? And if you have thought about it, if this has bothered you, I would say you resolve it yourself, because it took several years for me to resolve the difference between the comma there and the semicolon there, okay? And that is what the going beyond Born-Oppenheimer approximation is all about. And Satyajit will tell you how important this Born-Oppenheimer-Huang expansion is. What is important is that, since we will not have enough time, we have the normally what you call the kinetic energy part for the nuclear motion, and this is the electronic Hamiltonian. This is the internuclear repulsion. This internuclear repulsion is an add-on which we add here and then define the electronic energy and the combination as a potential energy for nuclear motion, right? Now we are not talking about the potential energy for electronic motion, we are talking about the electronic energy, total electronic energy plus the internuclear repulsion. This is called the potential energy. With Lodhraj, we wrote a paper saying why bother to add this repulsion term unnecessarily. You are complicating your life. You can always add it, it's exact. And so we will not have time to go into that, but these are nuances. But what is important is that what you see here is the total Hamiltonian, and you have the expansion in terms of the basis set here. These are the electronic basis functions, and I leave it to people like Soumyan and others to worry about how to develop a DFT for the non-adiabatic systems, right? But that is their problem, not my problem. So this is a standard recipe in quantum mechanics. Whichever course that you have taken in IIT Madras or somewhere else, you would have learned that the unknown function should be expanded in terms of a complete set of basis function. It always bothered me. I don't know how these coefficients, how do I determine them? Of course, there are ways of determining the coefficients, but that is the challenge, right? When you do a Fourier series analysis, and do an analysis, you need to still find out the coefficients, right? That is where the challenge is. So similarly here the challenge is in determining the coefficients, but still this principle helps us to arrive at working relationships. And let us get to the working relationship. We can skip a lot of algebra. And here is the working relationship. You have the kinetic energy term, and here is the non-adiabatic coupling terms. If you have two electronic states, the two electronic states can be coupled or not coupled, depends on the situation. Then this is the non-adiabatic coupling term. This is a first order non-adiabatic coupling. This is a second order non-adiabatic coupling. We unfortunately don't have time to go through the details of how we arrive at it. If you are interested, check with Sathyamurthy. He can give not one lecture, he has to give several lectures to do all this justice. But the most important part is that this first order non-adiabatic coupling term has a denominator which is the energy difference between two states. If the two states are far apart, infinitely apart, then there is no problem, this is infinity, the non-adiabatic coupling is 0. But when they become degenerate, you have a problem. That is when you have a conical intersection. Now all this we are doing in what is called adiabatic representation. The brilliant approach of Michael Bayer, Satyajit can correct me on that, was to go into the diabatic one. As a students or as earlier times, we used to have approximate methods of, if you remember John Murrell's paper, Sanjay, where we were using only approximation. Non-adiabatic coupling will be maximum at the crossing point, it will die down to 0 when you go asymptotically, whereas here you can work it out algebraically and you can work it out quantitatively. So once you do that, basically the problem is the denominator, which makes this a singularity, okay? I don't think Satyajit ever gets tired of emphasizing how this singularity is there, and the whole strategy is to how to circumvent the singularity. Those of you who have done the Cauchy residual theorem, you would go around the singularity, okay? Those of you are not familiar with the mathematical jargon, don't worry about it, okay? But what is important is that you end up with a conical intersection. Now here is an illustration of a conical intersection. For a paper that we published, you can see Satyajit Adhikari and Michael Bayer are co-authors here, his students are there as co-authors. This system where you have a DH2 plus, okay? DH2 plus is a isotopomer of H3 plus, which is fundamentally very important species. You think of H2 plus, it is a 1 electron covalent bond. H2, 2 electron covalent bond. H3 plus, 3 nuclei, 2 electron. The covalent bond you can still connect between the two. It's very much like your cyclopropene ion, right? It's there it is a Huckel treatment, pi electrons. Here it is a sigma electrons. H3 plus, and it is fundamentally very important. The first species to be formed, from what we understand, in the early universe, the covalent bond was helium H plus. But when Sanjay and I looked at this problem, we didn't know about all these things. This only in recent times I learned that the first covalent bond to be formed in the universe, if you believe in the Big Bang and what followed, was a helium H plus. It was not H2 plus, it was not H2. Now that mechanism requires another lecture some other time. When I come to IIT Madras, I can talk about it. Here what you have is two states of the same symmetry. They cannot cross each other, therefore there is an avoided crossing in one dimension, and here you have a conical intersection. And this is the one-dimensional problem, sodium iodide problem. One of the important problems that Ahmed Zoil worked on with his femtochemistry. Unfortunately, we don't have time. There is one can spend a lecture, one full hour on discussing the dynamics, the ground state to the excited state, dynamics, tunneling here, non-adiabatic coupling, Landau-Zener transition probability, all that, and how to detect it experimentally, verify it experimentally. That's what Ahmed Zuhail did with his femtosecond spectroscopy. When I went to Mexico City, because people normally talk about the Mexican hat. I said, what is so special about Mexican hat? What has that got to do with the conical intersection? So I decided, I didn't buy one, but I took a picture. So this is how a conical intersection would go. If you draw a straight line from here to here, straight line from here to here, of course, you have to bring them together to actually illustrate the conical intersection. So that is how it looks like. Now we come to the dynamics. It's an old story, almost 60-year-old story, experimental demonstration of vibrational enhancement for this reaction, helium and H2 plus, and forming a helium H plus. It may sound strange. Look, you have a H2 plus here going to helium H plus, but in reality, it is the reverse reaction that is fundamentally important. That is, there is no barrier between the two. They can go down the hill and form H2 plus. One of the ways of forming H2 plus, after it forms H2 plus, it can collide with H2, form a H3 plus. Okay, that's another aspect of it. Now, this system, how am I doing, Raj? Fine. So here is the set of electronic states for helium H2 plus. Most of our time, for almost 50 years, we spent on the dynamics in this ground state surface, right? We always use, and right in the beginning of the paper, we would write, I think Sanjay's paper, whether we wrote or not, we would say, since the excited state is much higher in energy, we look at the dynamics in the ground electronic state, saying that the excited state is not so important. 50 years later, Satyajit demonstrated how that large energy cap can still play an important role. And this is the potential energy surface. We had plotted it, I don't know how many times we have plotted it in the last 50 years. This was plotted by Satyajit and his students. How the potential energy surface looks like. There is a minimum here. There is a helium H2 plus species is there. This is actually a state where a system for which you cannot define transition state in the traditional sense. Transition state, you know, you'd have to have a saddle. There is no saddle here. You come from here, helium and H2 plus from here, you go into a well here, and you come over there to the products. The barrier for the reaction is the same as endothermicity. You cannot identify a saddle point, but you can pretend a transition state. And when you pretend, then of course all kinds of questions come. Nothing sank, nothing. So what is that? What do you call it? Holy or there's another word for nothing. Sacrosanct. Thank you. Sacrosanct about the saddle point. They did not know where to draw the line, so they used that saddle point as the dividing line back to Eyring, Polanyi, and so on and so forth. Okay, so this whole system for which is a very interesting result was published in Michael Bayer by 1976 or so, 74, 75. I lost the end point here, I'm sorry about it. And there they found out quantum calculation showed oscillations in the reaction probability. That is what drew my attention for 50 years now. I have been working with this system. And there is a problem. What happened? I seem to have lost. Well, so one of the early students of mine in IIT Kanpur, much before Sanjay came, was Tommy Joseph. He fitted the potential energy surface for the helium H2 plus system and carried out dynamics. At that time, it was a very important result. We managed to get a publication as a communication in the Journal of Chemical Physics. And so in the literature, it is known as a McLaughlin, Thomson, Joseph, Sathyamurthy surface. Has been studied extensively for a long time. And the oscillations that you saw a few slides earlier, right? These oscillations were rediscovered on the surface that was developed by Joseph Sathyamurthy. And this was, Joseph also identified some peaks here. There were many more peaks than what Michael Bayer had originally found. So we wrote a paper together and we explained these resonances in terms of quasi-bound states. These were identified as a Feshbach resonances, okay? But we have no time to talk about them. And when Sanjay was a student, he wanted to see if those resonances could be captured in the laboratory in a molecular beam experiment. Somebody did molecular beam experiment, so he undertook a lot of calculations. I think bulk of your thesis was on that. I still have his lab notebook, and I don't know whether he keeps a copy or not. I have. If he wants, he can always borrow it from me. And but finally, if the energy resolution was not good enough to show if the resonances actually exist or not. So we did lots of things. Now, here is the, since quantum dynamics, I hope this makes you happy. One of the early pictures that came out of the lab in IIT Kanpur to illustrate the wave packet dynamics for the helium H2 plus collision. What you saw here was the initial condition as a Gaussian wave packet. It moves along the reaction coordinate, and that is the potential well. And I told you there is no transition, there is no saddle point, but the repulsive wall here is important. It reflects the incoming wave packet. Part of it goes into the product channel, part of it comes back here. You can analyze this by a Fourier transform and determine vibrational state distribution. You can calculate the reaction probability. In this case, you can see half of it has gone into products, half of it has come back. It means approximately the reaction probability is 0.5. But if you do energy resolution, you can find lots of peaks. One of the students who came, Ashwini, who is a professor in IISER Kolkata, was not happy with those collinear geometry, two-dimensional. He wanted to work with the 3 dimensions. And I think Aditya was also involved in this, in making this. These were made the way Disney made his cartoons, right? Or Mickey Mouse kind. You make frame by frame and you make it run. Today, of course, the technology enables you to do much better than this and faster than this. But fundamentally, it's important, it conveys the message how the wave packet dynamics is there for the system. Now, we did all that stuff. We did a lot of calculations, showed agreement between experiment and theory, but we were partly cheating. Partly cheating in the sense we put an error bar on our calculations, put an error bar on the experimental results, and say the error bars match, therefore we are in agreement with the theory and experiment agree. But that was not strictly true, and it became clear when Satyajit entered the picture. Here you can see, to give you an idea, here are the experimental results from different groups. Chupka and Russell 1964, Tang et al. Was 2007 or so. Over a period of 40 years, where different people had done various experiments, qualitative agreement, no quantitative agreement. And many of us, including Sanjay's results are somewhere here, okay? And some other people from our lab had done some. Tipanda, he's a professor at IIT Guwahati, so he got this result. And every time we would say that, our results are in reasonable agreement with the experiment, right? But strictly speaking, they were not. So we had to make this plot for the paper that we wrote together. I am not overlapping with any of your stuff, right? Okay. So enter, I told you Michael came, and then we started the collaboration, and I have already told you this one, how the excited state is there. And we looked at collinear helium H2 plus. There are so many conical intersections. These are the yellow ones are all undergraduates. And this is a PhD student, not mine, but some of my colleagues, PhD student. All 3 of them were students in the course offered by Michael Bayer, and there are a couple of more students, and they also wrote papers on non-adiabatic coupling. Now, there are ways and means of proving. Satyajit is an expert. The results are from his lab. So we'll skip all those slides. And because if there is a conical intersection, if you go around it, you will gain geometric phase. Is that okay? Geometric phase? Because there is a subtle almost. He says, see, almost. A geometric phase. These are details of the system, how there are avoided crossing between the excited state and the ground state, etc. But finally, what is important is that you treat 2 surfaces, ground state and the first excited, include non-adiabatic coupling, and carry out the dynamics. The reaction probability plotted as a function of energy, and you can say the present adiabatic calculation, present diabatic calculation. Adiabatic calculation means you don't worry about the non-adiabatic coupling. the diabatic representation, use it and include the non-adiabatic coupling, and you get the results. You get reaction probability as a function of orbital angular momentum. The results look dramatically different. This is dominated by large L values, dominated by not so large L values. But you have to do an L averaging to get what is called a cross-section, measurable quantity in the laboratory. When you do that, now you can see the experimental results are all here. This dark line is what Satyajit and his students got by doing a two-state diabatic dynamics. Now we can say, without hiding anywhere, that theory is in agreement with experiment. So the moral of the story is that you may pretend the non-adiabatic couplings are not important. You may pretend that the excited state is very high in energy. But if you actually do the dynamics and actually incorporate the non-adiabatic coupling, you will find some surprises. And that's what we found. And this caption here I borrow from Saurav Paul, who gave a lecture on Monday, Tuesday. He always says, I've got right results for the right reason. Okay. Some of the earlier right results were for not so right reason, not for wrong. We didn't do anything wrong, but it was not good enough. So now we have taken all the factors that are responsible for the quantum dynamics. And I told at that time to Satyajit, actually, it's a difficult problem was dealing with the ground vibrational state of H2 plus. If only they had done H2 plus V equal to 1, the cross sections would have been larger, the effects would have been much more significant, easily traceable. So he wrote a paper recently. So I wrote this as the latest, where he considers the V equal to 1 state also. Vibrational enhancement is a very fundamental property of this system, and that is shown by his detailed quantum calculations. So when I prepared, that was the latest, right? Still it is the latest, but then we have submitted a paper where we do the classical analog. Ground state, first excited state, non-adiabatic coupling, you treat all of them classically in the classical mechanics, and you get results which are in agreement with the experiment, right? So that is still not published. We have it's under review. Tonight we are supposed to finalize all the revision of the manuscript. So what I have done is to take one system as an illustration on which Sanjay started his PhD thesis work. And we have carried on, you graduated in 1990? 90? 93, okay. 2026, another 33 years later. The system is still of interest, dynamics is still of interest, and there are fundamental aspects of it which are very important. And it is important to know what these nuances are. Yeah. With that, I want to thank you for inviting me and giving me an opportunity to give this talk.
Thank you, Prof. Sathyamurthy, for the nice talk.
Stay within the time, right?
Yes. We have time for a few questions. I think we can start with the students first.
Nowadays they talk about inverted classroom, right? Do you try this model in IIT Madras? But we all know about it. Huh? So where you are supposed to take the lead. Oh, he has gone. All right. So where, yeah, for a small classroom, it actually works very well. We had in the early years of ISR Mohali, students came and complained about a course, humanities. Why are we learning humanities? I talked to the instructor and said, why don't you make, in the business school is very common. You have a case study, you have a group discussion, etc. Why don't you convert your classroom into that? So I divided the class into 5 groups, 5 tables. And the next day, sir, we had a fantastic class. We didn't know that it is so interesting. So the reason I said was in the inverted classroom, you are supposed to be in the front, ask questions, give answers, and we are there to help you. Still no questions? In such cases, I say you send an email to me, okay? Some people do.
This is not a question, comment. And I want to hear your opinion. that we know the three things impossible to handle except quantum mechanics. That is 0 point energy, tunneling, and non-adiabatic. But we are attempting here non-adiabatic. You are a part, and I am also part. It matches quite well in the experiment. But what is your comment that, I mean, how we will have future if say that the handling of this quantum friction, and in future how it will work, and I mean, what is your inner guess? I mean,
Yeah. See, let me answer the question first, the lighter side. You know, anybody from Kerala here? Any Nambudiri here? Right? Okay. So there are, so you know, it's a joke. I'm not. If I didn't say Nambudiri, it did not matter. The joke would still remain the same. The fellow was.
joke is invariant.
Yeah, the joke is invariant. You know, so some people don't like, you know, the identity, right? The fellow was looking for something under the lamp. So somebody asked, "What are you looking for?" He said, "Oh, I'm looking for the key." He said, "Oh, how did you lose? Or where did you lose?" "Oh, I lost it there." He said, "Why are you looking here?" "That is because there is light here," right? So in science, to some extent, we do this actually. The potential energy surface calculation was very difficult. In my days, when I was submitted my thesis, generating 100 points, 200 points was a big deal. I think Lurdraj, for the same thing, right? You did helium F2, right? So how many points you had? 300, 400 points?
400.
400 points. Today, he and his students deal with 40, 50,000 points generated of a potential energy surface, but then he is in keeping with the times, right? What is the machine learning? He uses the machine learning tools to make use of the information of 40, 50,000 points. We didn't have that privilege. We could only guess the feature of the surface with a few points, maybe a few 100 points. But today, we want to know all the details. It's almost like looking at a bride or a bridegroom's picture. You know, the Dadima wants to look at all the details. Uska face kaisa hai, na ye, you know, all that kind of. So we want to look at the details of the potential energy surface, because every little feature of the surface, saddle point, potential well, barrier, the width of the barrier, everything is important to decide the dynamics. But when you don't have the wherewithal, put yourself 100 years ago. When people were trying to predict chemical, 1927, was it a H plus H2 experiment? Approximately 27, 28, at Farkas paper. And Polanyi and Wegener, 1930, wrote the paper on the transition state theory. People normally do not know about Wegener. They think about Eyring and Polanyi. That came 1931, subsequently. They had no way of finding out how to determine the rate of a reaction. They said, all right, choose the saddle point, draw a line, anything on this surface is reactant, anything on that surface side is the product. They knew how to calculate partition function. So they still did not know the transition state. They knew the transition state structure, but they did not know the frequencies. Guess, put some reasonable numbers. My friend in Kanpur used to call engineer's approximation, right? I want to build a bridge. So if it is all pure sand, what it takes. If it is all pure cement, what it takes. If we have ACC or Adani ACC cement, how much does it take? You have to come up with an estimate before you can float a tender, right? So coming back to this, you do many things that is possible technologically at that point in time. When classical mechanics trajectory calculations were started, one of the early calculations, apparently, you know, you stop me whenever time, okay? I have already exceeded my time, right? But, you know, he is a very nice guy. So he feels shy in stopping me. But certain stories you must learn, must hear about. Eyring, when he went back to Princeton from Berlin, along with the Topley and Hirschfelder, there are no computer, no calculators. So they said, let's go to the football field in Princeton, football ground. They wanted to mark potential energy contours, kick a ball and see how it goes and map it. That was not done. But that was a basic idea. When you have nothing else to do, right? I mean, there is no other technology available. Make use of the best technology available. So 1965, 66, Karplus, Porter, Sharma wrote a classic paper. Eventually, Karplus abandoned this, used the approach, went on to look at biomolecules, proteins, and nucleic acid, etc., and he got a Nobel Prize. If he had stayed with the H plus H2, probably he would not have gotten the Nobel Prize. But they knew there is a 0-point leak in those trajectories, but they didn't worry about it. In the absence of anything, let us get an estimate. Tunneling, people knew. Low temperature tunneling is important, so don't do low temperature kinetics. But today, if you deal with interstellar medium, as Dilip is there, he writes papers in journals of astrophysical interest. So there, low temperatures tunneling is important. You cannot do away with it. And the third one was non-adiabatic. Today, the quantum chemistry technology enables you. Today, MolPro routinely gives you non-adiabatic coupling. You still have to do some massaging of the data to get the right picture. It's possible. So today, you can, Sanjay tried to do is to prevent the leak. So what do you do to prevent a leak? You put a barrier there. But putting a barrier has its effects. It makes an oscillator. There is an oscillator vibrating like this, but if you put a little bump here, then it becomes a kicked oscillator. Or it can be a kicked oscillator, or it can become a damped oscillator. So the results were unrealistic. So simplest was to throw away all the leaky trajectories, because that's what we could do at that point in time. So I have answered all of them. Leaky trajectories, tunneling, that we have tunneling, and non-adiabatic coupling. So do the best possible calculation given the knowledge and technology at that point. Thank you.